So this is section 1.4, diode circuits and AC equivalent circuit. So what they're showing is we have a AC signal VI, and we also have a DC signal from a power supply VPS, and put a little note here. And this is going to be our input signal VI. And then we have a diode. It's a PN junction, forward bias, and this is VD. And then we have a resistor. And then this is plus, minus. And here's our resistor. And our output is going to be taken across the resistor. So this is V out. And so how do we analyze the signal? And throughout what I've found in the book so far is you have a procedure for these DC and AC mixed signals, is that you do a DC analysis first, do DC only analysis, and then you do an AC only analysis. And so if we get rid of all the DC signal, get rid of all the AC stuff and do the DC analysis only, we look at all the components in the DC realm. So we got plus minus V power supply, plus minus VD, and then R, and then this is our output, V out. And so we're just going to do an analysis on this signal. So this is our AC only, our DC only, DC only circuit. And then we do an AC only circuit. And so we just have VI. And we're going to analyze these separately. And then to represent the diode in DC, we represent it by AC. We represent it by a resistor RD, and RD is equal to 1 over GD, which is equal to VT, which is our thermal voltage, that's 0.026 volts, over I dQ. And this is, again, our output right here, our small signal output. And so RD is equal to the small signal resistance. So small signal resistance. And GD is what they call the small signal incremental conductance. Small signal incremental conductance. That's G sub D. And or you could call this equal to the diffusion resistance. And GD can likely be called the diffusion conductance. Okay, and so this IDQ is the current, they call it the DQ, DC quiescence current. And that's this current here, IDQ. So you have to do the DC only analysis to get to figure out what this resistance is in the AC circuit, which is basically your thermal voltage over IDQ, and then you got IDQ from the DC circuit. So now we're going to do example 1.11 in the book, where they want to analyze circuit in figure 1.35. And they want to know what the V out is. And so that was that circuit I just previously drew, and but they give you parameters now where this small signal is 0.1 sine omega t, and the power supply is equal to 5 volts, and we're told that this is 0.6 volts across the diode, and this resistor is equal to 5 kilo ohm. And again, this is our V out. And so we have to do the DC analysis only first. And so this was 5, and this was 5 kV. And so we just do KVL at this point, Kirchhoff voltage law. And so we get 5 equals 0.6 plus I dq 5,000. Okay? And so we have I dq is equal to 4.4 over 5,000, which comes out to be 0.88 milliamps. And that means our V out is going to be equal to 5,000 times 0.00088, which comes out to be 4.4 volts. So this was the number 1 step, DC only analysis. And then your number 2 step was you do the AC circuit, where we have the plus minus 0.1 sine omega t, and then we have the RD, which was VT over IDQ, which is equal to 0.026 over 0.88 milliamps, okay? Which comes out to be 29.5 ohms. So 29.5, and then we have our 5,000, and we have our V out for the small signal. And again, we just do KVL, where this is our I at this point. We call it ID. So ID is going to equal, we got 0.1 sine omega t equals basically ID times 29.5 plus 5,000. And so ID is going to equal 0.1 over 29 plus 5,000 times sine omega t. So ID is equal to 19.88 sine omega t milliamps. And then if you wanted to do your V out, your little V out, you just say it's 5,000 times this 19.88 sine omega t milliamps, which comes out to be 0.099 sine omega t. So that's our small signal output. And then your total output is just going to be that big V0, where to go, this one, plus this one here. And so you have your DC with this sinusoidal superimposed on top of it. The next part of it, of the chapter, goes into the frequency response, and it's very skimpy. It doesn't really go into detail, and so they go into the frequency response. And basically, you have this what they call the diffusion capacitance. And it's equal to dq dvd, and it's basic, and so the diffusion capacitance represents the change in stored minority carriers caused by a change in voltage. And they present a graph in the book, and you have your depletion region here, and this is the minority carrier. So if this was a p and this was an n, this would be your holes and this would be your electrons. And they're saying as you have this small signal going through it, this is going to fluctuate. And so I'm just drawing over time. It's going to, the small signal is going to increase it or decrease it depending on the polarity of it. And so this is where this diffusion capacitance comes from. And then in section 1.4.2 they present this formula where you have the admittance is equal to GD, that should be G sub D, G sub D plus J omega CD. And they present, a model where for the small signal, where you have RD in parallel with this CD, this diffusion capacitance. And how they really get the formula. If you put this into the frequency domain, well, the resistor doesn't change in the frequency domain, so we just leave it RD, and the capacitor you would call 1 over J omega CD, okay? And then if you wanted to add up all the admittances for a parallel circuit, the admittance is 1 plus y1 plus y2 plus y3 whatever's in parallel. And so for a resistor, this is 1 over RD, and this would be 1 over J omega CD. And so 1 over RD, we said in the previous slide, is equal to GD. Then 1 over is just going to be J omega CD. So that's where they get that formula, by just adding up the admittances. So in section 1.5, they talk about other types of diodes. And the others are, the first one in section 1.5 is the solar cells. And you have a PN junction. So we have our good friend, the PN junction. It has the depletion region. I'll just call it depletion region here. And then we have the N region, okay? And then we have, there's no bias applied. There's just the external load, whatever you're trying to drive here. And then solar light, I'll just call it H nu, comes in and hits the depletion region, generating holes and electrons. So we'll just write the process. No external voltage applied. Light hits the space charge region and creates a electron hole pair that is swept out of the region to generate current. Okay? And then current produces a voltage across the load. So that's the solar cell. The next one, in this other type, in 1.5.2 is what they call the photodiode. And what a photodiode does is it converts optical signal into electrical signal. And so that's number one. Number two, it operates in reverse bias. So again, we have the P, and we have the depletion region, and then we have the N, and then some light comes in and hits it, and this is reverse bias, so small, big, and this is minus, plus, so reverse biased. So that's all they say about the photodiode. And then in section 1.5.3, they talk about the light emitting diode, or LED. And what an LED does is it converts current into light. Okay? And it is ran in forward bias. And holes and electrons flow across the space charge region and become excess carriers. Holes and electrons flow across the space charge region and become excess carriers. Whoops. Okay, that's number 4 in the process. Excess minority carriers recombine with the majority carriers in the neutral semiconductor region. In the neutral whoops. Neutral semiconductor region. Okay, and so two things can happen here: a direct band gap material, such as gallium arsenide. Electrons and holes recombine with no change in momentum. With no change in momentum. And a photon is emitted. Okay, so that's the giving off of light. And then we have the other guy, which is a indirect band gap material, such as silicon. Both energy and momentum are conserved, and so no photon is emitted. But that's not an LED. And lastly, the number 5 here, the output intensity of your LED is directly proportional to the diode current. Okay, so we have the LED converts current into light. It is ran in forward bias mode. The holes in electron flow across the space charge region and become excess minority carriers. The excess minority carriers combine with the majority carriers in the neutral semiconductor region. So that's important. Neutral semiconductor region. And then in an LED, and so I'm just going to put a box around this one because this is really not what we're interested in. So an LED consists of a direct bandgap material, such as gallium arsenide, where holes and electrons recombine with no change in momentum and a photon is emitted. And lastly, the output intensity is directly proportional to the diode current. And so that's another one that's kind of important too, because I know a few people that use laser diodes, and the power supplies for the laser diodes are quite expensive because the current has to be highly regulated because they're usually doing some type of quantitative measurement with these things. And next, in section 1.5.4, they talk about, and I don't know how to spell this, the Schottky barrier diode, which is the same thing as a Schottky diode. And they show a picture of it. It's like a barrel, and it has a metal, usually aluminum end. So it's not like a p-n junction, it's a metal n junction. So this is n-type semiconductor. And so this is your diode current ID, and this is plus and minus, okay? And this would be, the whole thing would be VD. And the symbol looks like this, where you have a regular diode, and then you just throw on these little sticks on the end of it. So that's the Schottky diode. And in it, they basically say that the current mechanism is different than a p-n junction diode. The current in the Schottky diode results from the flow of majority carriers over the potential barrier at the metallurgical junction. So it's not the minority carriers, it's the majority carriers. And the implication of this is that there's no minority carrier storage, and which results in fast switching times. Essentially, TS is approximately equal to 0, and we talked about TS previously. And so if we look at a curve, and they present this in the book, of ID versus VD, and then for the Schottky one, I should say, versus the PN. So this is the PN, this is the Schottky one. So you have a much lower turn-on voltage than a PN junction. And so if we look at the reverse bias current for a PN, it's about 10 to the minus 12 amps, whereas for the Schottky barrier one, we'll just call this SB, and then we'll call this one PN. It's lower, minus 8, a larger current. And for a 1 milliamp ID, VD is equal to about 0.539 volts for a PN, or the VD for the Schottky barrier is 0.299, so about half. So it's less turn-on voltage and faster switching for the barrier diode. And the last diode that they talk about in the end of the chapter 1.5.5 is the Zener, I don't know if it's Zener or Zener diode. And if we draw an ID curve, this is I, this is VD, increasing. And so for a PN, we have going up, but for the Zener diode, we have a reverse bias current, and its slope is 1 over RZ, and we call this right here the breakdown voltage, breakdown. So these Zener diodes are operated in reverse bias. And the symbol, they look like a little squiggly line here. And so they're operated in reverse bias. And so the important thing about the Zener diodes is they're fabricated to have a specific breakdown voltage. And they're used, or can be used, as a constant voltage reference, since they're fabricated to have a specific breakdown voltage. And so example 1.13, they want you to find R, and you're given that this is a 10-volt power supply, and we don't know what R is, but our Zener diode is in reverse bias, and they tell you that the VZ is 5.6, so that's fixed. They also tell you that RZ is equal to 0. Okay, so this slope is basically just straight down. So the voltage is constant over the course. And you do KVL again. That's almost all circuit analysis. It always ends up being doing KVL or KCL with a few other twists thrown in once in a while. So you got 10 equals, and you just need to figure out what I is here. IR plus 5.6. So, oh, they tell you as a given when I is equal to 3 milliamps. So they give you the I here is 3 times 10 to the minus 3. So you just solve for R is equal to 10 minus 5.6 over 3 times 10 to the minus 3, which equals 1.47 kilo ohms. So that's it. End of the chapter.